Hi. This video, I want to talk a little bit more about simulation of random numbers. Generating these pseudo-random numbers is an important input to the Monte Carlo simulations, and there's a few other pieces we can fill in. So first is a quick note about built-in functions. So MATLAB has got a number of functions for generating directly random variables from a number of distributions. So I've got a list here on the right side of the slide. And those are fine. We have to, just the usual caution, be careful about the parameters that you're inputting into those to make sure you're actually getting the distribution shape that you're intending, because there's oftentimes more than one way that the parameters can be defined for a probability distribution. Probably more interesting is to note down at the bottom, there is a built-in function for generating multivariate normal random variables. So these are following the multivariate normal distribution that we've used a lot in this class. And you can specify the covariance matrix and simulate random variables with dependence among them. So that's a pretty useful function that we can lean on a lot. And a lot of other numerical libraries have similar sets of functions that can generate random numbers directly. That said, the inverse method is a nice general technique that if we've got something that's a little out of the box, we can use that for generating our numbers. Let's talk about multivariate random numbers, though, for a little bit. That's obviously a really important distribution for this class. And if we want to generate those things ourselves, we actually can using some of the concepts from class. So that's a nice connection to some earlier stuff. In order to do this, we're going to need a mean vector, M, and we're going to need a covariance matrix, sigma. And so we're going to specify those things and say, now I'd like samples from random variables that have that mean vector and covariance matrix. So the way we can do that is actually to take advantage of this transformation we've been using in a lot of different contexts. First, we would want to generate n independent random variables, where n is the number of random variables we're ultimately hoping to end up with. We can generate independent standard normal random variables. So to do this, we can just use basic inverse method, generating uniform random numbers and then putting them through an inverse standard normal CDF. And so we could call that vector small u, a sample. And then we could put that small u into our same transformation that we've been using in a bunch of other contexts. We can take that u, multiply it on the left by an L matrix that'll introduce the correlation among the components, multiply by the D matrix, that'll introduce the standard deviation that we'd like, and then add M, that'll give us the right mean value. Okay. So that's a cool trick. And it's basically the same math we've been using in a bunch of other contexts. So that's a nice, easy way to do this. And pretty fast as well, right? It's just a bunch of linear operations. So there's no complicated calculations that go on in there. Come back to an example later. I think we can actually, this is a little bit redundant with what we just talked about. More generally, if I want random variables with dependence, but that don't have a normal distribution, we could think about that in the top distribution and say, let me simulate some random variables that have correlations and have the marginal distributions I'd like. So the way I could do that is if I've got kind of the marginal CDFs f of xi, and that's ultimately what I want the marginal distribution to have, but I also have a correlation coefficient matrix. Those are the two things that I'm going to need to generate these things. First, I'm going to put in the correlation, and then second, I'm going to give the simulations the marginal distributions that I like. Okay, so I'm going to do the same thing 2 slides ago. So I'm going to generate the independent standard normal random variables. We'll call those u. And then I can multiply those on the left by L naught, where that's the lower triangular matrix from the Kleski decomposition of the correlation matrix we want. And that could either be the modified correlation coefficient matrix that we talked about in section 7, or it could just be the R as an approximation of the R naught. So that'll give us Z's, which are multivariate normal, and they have the correlation matrix that we would like. The means are still 0. We haven't introduced any mean values. And the covariance matrix is just this R naught matrix, right? So it has standard deviations of 1, just has correlation in it. But then we could take those and we can put those into a transformation. So we'll take the Z's, put them into the standard normal CDF. That'll make them uniformly distributed, right? So any random variable sample going into its own CDF is going to become a sample of a uniform distribution between 0 and 1. And then we can just use standard inverse method back through the inverse CDF of the target distribution, and that'll give us a sample of xi. So that'll have the target marginal distribution f of xi, and it will have correlation between elements because of this step we went through to go through Z and introduce that correlation. Okay? So that's a pretty convenient technique. There's nothing really out of the ordinary here, right? Inverse method in the bottom line, but just a step before that to introduce some correlation. Okay, if that still doesn't work and we want something even more general, we can go to the Rosenblatt transformation that we used for kind of our case 4. So you can see there's a lot of overlap here with the transformations we used in form, right? As long as we can get samples in kind of standard normal space, then we can just use those same transformations form to get ourselves into an arbitrary joint distribution. So we can piggyback on all that math we developed earlier. Okay, so this one, if we've got a joint PDF that's an arbitrary distribution here, f of x, and we want to generate samples from that, what we can do is we're going to first start from uniform variables, so we don't have to go through normal space this time. So these are uniform. I'll call them y. And then we're going to sequentially apply this Rosenblatt transformation to each term. So for the x1, the first component of this thing, we'll just do standard inverse method. Or I'll call it basic inverse method. And then for the second component, x2, when I generate that sample, I'm going to use the inverse CDF for x2, but conditional on the value of x1 that I sampled in the first row here. We're going to basically take that joint distribution, we'll sample one of the terms marginally, and then once we've got that sample, we'll sample the other one conditional on the sample from x1. And so on. And then so the third component will be conditional on the first two, and so on. So this is possible, but it's very slow. You've got to do a lot of inverse conditional CDF calculations. So it's not something I think I've ever actually done myself for a project, but it is feasible and it's available if there's a very specific distribution that we want. Okay, so that's a few more notes on simulating random numbers. The multivariate normal and the TOF samples are probably the most interesting ones out of this. So let's finish with the first set of conclusions on Monte Carlo simulation. So we've introduced this flexible approach to just sample numbers and check failures or non-failures. We've worked through the math and convinced ourselves that we do get a probability of failure estimate. Doesn't require linearization or approximations. It does have some sampling error, and we looked at the variance of our estimator depending on the number of samples we generate and this probability of failure and things like that. And so that's really the challenge we have to face here. Specifically, we saw that the number of simulations that we need to produce an acceptably accurate result, the challenge, that number is going to get bigger as the probability of failure gets smaller. But when we're working in the domain of small probabilities of failure, we've got a challenge there. Our analytical solutions don't have any challenges with small probabilities of failure. So form is appealing in that regard. On the other hand, this Monte Carlo computational expense was independent of the number of random variables in the problem. That really is an advantage, and particularly when we get to problems with very large numbers of random variables, Monte Carlo gets appealing, and problems where the linearization would introduce a large approximation, Monte Carlo gets appealing. So there's some cases where this is really an appealing strategy. Given that probability of failure problem, then we talked about importance sampling. So that was a really important extension in reliability analysis because it's going to compensate for the small probability of failure challenge. And further, we've got this form result that helps us develop that importance sampling distribution. If we didn't have form ahead of time, we'd be in the dark a little bit of how to do this importance sampling. And the pairing of form with importance sampling is a really nice combination that does arise often. And then a final note here is that with form and our second moment methods, we got design points and importance vectors, gamma, and things like that, that gave us some extra diagnostics of variable importance, and things like that. We don't get that out of Monte Carlo naturally. You can sometimes post-process your results and try to get a little bit of information of that type, but it's a lot more effort and a little less elegant. In the end, kind of form and Monte Carlo both have nice features that make it often the case where we might want to just do both of them rather than pick one or the other. And take advantage of the complementary benefits of the two. Okay, so that's the first set of notes on Monte Carlo methods, and those are the methods we're really going to lean on in this class. I'm going to give you a few more follow-up videos just to talk about some other sampling approaches and give a little bit broader context for what's possible in this realm of analysis. But that's it for now.